see how this works, guys. So we're just trying a whole bunch of new things and see what sticks. Yes, right. Okay, guys. So this time we're going to be working with timer units, and this is when once you start learning timer units, this is when you really become dangerous when it comes to microcontrollers, because now you can start doing all kinds of really cool applications once the timer units are in. The 18F4520 has 4 timer units. They're just named by number, so they call it timer 0, 1, 2, and 3. Here is what the microchip pick shines when it comes to ease of use. These timer units are very simple to use. And so if you think about these timers and you compare them again on other manufacturers like Atmel or Freescale, Motorola, their timer units are way more powerful, but they're actually really difficult to use compared to this. And so I think this is going to give us a very easy time today. This is not very complicated, which is the good news. Okay? There are 4 units, like I said. They're all labeled by number, timer 0, 1, 2, and 3. And we're going to be learning 4 modes of operation. Not every single one of these timer units respond to all 4 modes. And so we're going to be learning overflow capture, compare, and pulse width modulation. And so all of these 4 ideas are all related to a timing unit in one way or another, okay? Today, we're going to spend our time in the overflow circuit. So this kind of like gives you the idea of what's going to happen in the next 4 weeks. So we're going to take about 1 week per system. So it's going to be overflow, then we're going to spend some time in capture, compare, and then finally we'll end up with pulse width modulation. By the time we're done with PWM, we're going to start now trying to venture a little bit into control systems. How do I go about using this microprocessor to control something, whatever that is, all right? So that's the idea behind it. The other thing that is interesting and we're going to be studying today is the ability to interrupt based on overflows. And that is one of the best features that this circuit has. The 18F4520 is going to give you interrupt support for capture, interrupt support for compare, and interrupt support for overflow. But there is no interrupt support for pulse width modulation. So pulse width modulation is, in some sense, the easiest circuit to set up in this micro. By far. It's one of the easiest systems to put up. So anyway, so today we're going to be working on timer 0 and timer 1, looking at the overflow circuit. All right, so that's the idea behind it. So here we go. Here is timer 0. Timer 0 is a circuit. Okay, so for those of you who took Digital 2, in Digital 2, we created a clock. And in that clock, we had a 555, and that 555 was in fact controlled by, or it was controlling a counter, right? So we got a 555 and a counter. That's exactly what we have here. This is the exact same circuit, except that you don't have a 555. We replaced the 555 by the first 3 blocks that you see in here. So you have your crystal, a circuit that we're going to call the divide by 4 circuit. You have a pre-scaling circuit all together and in series. And together, these 3 boxes become the 555 circuit. This is my oscillator. Nothing more than an oscillator. And then you have these 2 boxes at the end. Those are my counters. This is exactly what the 193 used to do. You remember that? You either could put there a ripple counter or you could put there a universal counter. In this case, it's just a straight out counter. And so what is interesting is that the user has the ability to change the behavior of your pre-scaling circuit. So a piece of software will change how that little circuit behaves. And the user also has the ability to change the behavior of the counter. See that? And so we are nothing more than going back to Digital 2. That's why I'm saying that this is kind of like a simple idea. It's just nothing more than, let's take a look at a counter and see how we can just get this counter to work. That's about it. Now, there are 2 things that are important on a counter, and we actually studied this a little bit in Digital 2. One is what I call the update. So the update time is nothing more than the frequency or the period of the 555. You remember that? So if we were going to build a traffic light, the traffic light is a combination of how many counts your counter can handle, and at the same time, it's how many or how much time does it take for every count to show up, right? So in this case, we're going to calculate the update time, is how fast the timer is counting, and we're going to calculate the overflow time. It means how long does it take for that counter to fill up and go from the maximum number back to 0. And so that overflow time, these two values are the ones that pretty much determine the entire behavior of that circuit. So very simple idea. Is an oscillator connected to a counter, just like you guys did in Digital 2, except that you just bought it. It just comes already pre-done. That's all there is to it. Make sense? Okay. So there is two modes of operation. If you take a look at your prescale value, the important part to know about that prescale is that you can set that prescale, and prescaling is nothing more than a divide by. You remember how we did ripple counters in a divide by 2, ripple counters in a divide by 4, ripple counters in a divide by 8. You remember that? And so the user can make this a divide by 1, 2, 4, 8, 16, 32, 64, 128 to 56. That's all it means. It means that you, through software, you have the ability to make this counter a divide by whatever you want, as long as it is in powers of 2, from 1 all the way to 256. That's it. You don't have to change the circuit. You just have to send one command and the machine will change that divide by. All right? That's the idea. The other part that is interesting is that your timer, the actual counter, could be an 8-bit counter, but it could be a 16-bit counter. And it is all user selectable. So you send the command and you say, hey, I want my clock to be a divide by this amount, and I only want 8 bits. See that? So that means that if you just choose 8 bits, the machine is going to go from 0 to 255, and it's going to just blank back to 0. Right? If you choose 16 bits, the machine is going to go from 0 to 64,536, and then back to 0. Right? So the machine has the ability to just simply overflow. Does that make sense? Now, these registers that you're using in here are read-write in nature. You can write to them and you can read from them. But I think that for us at this moment, we should be just reading from them and never writing to them. It takes a little bit of skill to make sure that you write to them appropriately. So for now, let's just leave it at, let's just read from these timers and let's not do much more than that, all right? So we're going to be doing something very, very simple. If you want 16 bits, you're going to be using both the low and the high bits. So that means a total of 16 to get your entire circuit. Now, these divide bys, we're just chatting away, right? We just haven't done anything special. But these divide bys are nothing more than a divide by counter, the same way that you were using it in Digital 2. If you have a crystal at 20 megahertz, for example, a divide by 4 is going to block out a quarter of all this to make it 5 megahertz, right? So I am just blocking out. In other words, I'm picking one cycle per every 4 cycles, right? You're pretty much lowering down the speed at which the counter counts, and the prescaler is just dividing it even more by the PS amount. So you could make this a really small amount compared to your crystal, which means that we have to keep in mind that we are constrained to the values that we can take. So for example, this is the name of the registers that you gotta keep in mind. TMR high and TMR0 low. And this is the important part. So let's just, this is really the beginning, okay? So it goes like this. Timer 0 is driven by a crystal. You have a divide by 4 circuit. That divide by 4 circuit is going to drive your prescale circuit. This prescale circuit is controlled by the user, and this guy is going to drive my timer, okay? I'm going to call this guy timer 0, which can be 8 versus 60 bits, okay? Now here's the deal. The question that we all want to know right, is that these 3 boxes, I can replace those 3 boxes for an LM555 in the digital 2 example. So this is micro, and this is your digital 2. And this 555 is driving a 193. This 193 is a 4-bit counter. So this is a 4-bit counter. You remember that? Okay. In order for us to figure out how fast is the 193 moving, right? How fast is the 193 counting? What we did is that we step in here and we calculate the period of the signal that drives the counter. And we figured that out to be T high plus T low. Remember that? This was equal to 0.693 R1 plus R2 times C plus 0.693 R2 times C. Right? Kind of like flashback. This is what we used to do. And the reason why we are calculating all this stuff is because we wanted to know how fast is my counter counting. Okay? Now, what we're doing now is that we're replacing the 193 by somebody called Timer0. It's just a bigger 193. The 193 has 4 bits. This guy could have 8 or 16. So it's a very large counter, okay? Now, how fast is this guy being updating that guy? And the answer is the timer for the 0 cycle. So I'm going to call it 0C. So that's timer 0. The number of cycles, or how fast are these cycles showing up, is 4 times the prescale divided by the frequency of oscillation. All right? This prescale value is one of these values that the user has selected. So it's going to be either 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, and so on and so forth, right? In other words, this is going to be nothing more than I can divide by 1, I could divide by 2, I could divide by 4, I could divide by 8, and so on and so forth, okay? So this is the most important value that we need, this equation, because it's going to tell us how fast is this timer going to work. So for example, let's take an example.
What's the line over the T there?
Just 0.
No,
underneath the P 4 times prescale.
Oh no, this is an ugly F.
Okay.
Oh.
Some magical new symbol.
Some magical new symbol. It's a Spanish thing. All right, guys. So that's right. That's right. So check this out. All right. So if the user chooses a prescaler equal to 1 and a timer 0 with a number of bits equal to 8, right? The first question that I want to ask is, can you calculate the rate at which the counter cycles? Right? In other words, how often is timer 0 going to change? Right? The machine is going to go 1, 2, 3, 4. The question is, how often is that going to happen? All right, so the example asks for a prescaler equal to 1 and an aim equal to 8. We're going to make the assumption that the oscillation is 20 megahertz because this is what we've been using in class, right? So when I don't give you a frequency of oscillation, pick 20 megahertz, which is the crystal that we've been using in class, okay? All right, if that's the case, let's just calculate this quickly. We're going to have T0C is equal to 4 times 1 divided by 20 million. Right, so this is 4 divided by 2, that's 2, and then divided by 10, that's 0.2, so this is 0.2 microseconds. All right? This means that every 0.2 microseconds, the timer goes tick, right? 4 microseconds is gone twice. 6 microseconds, you have gone 3 times, or 0.6 microseconds, you've gone 3 times, and so on and so forth, right? So this is the update time, or the cycle time. And this is the first quantity that we really want, okay? So it goes like that, all right? So we put it in the slide so you can have it. I'm gonna go this way again. All right.
Just because this thing's dead.
All right. All right. So that's the calculation that we just did here. Okay. Now here's the second part. The second part of the game is not only how fast is this guy updating. I want to know how long does it take for my machine to overflow, right? So the question is, how much time does it take for this counter to overflow? And the answer is kind of obvious. So if I am calculating the time it takes for overflow, I'm going to call that T0F, all right? Timer 0 overflow time. Well, it is obviously going to be how fast is this guy counting times 2 to the power of n, which n is the number of bits, right? It could be 8 or it could be 16, depending on how the user chooses them, right? And that's the formula that you have in here. The time 0 of overflow is going to be timer 0 cycles times 2 to the power of n, where n is the user-selected number of bits. Remember that n can only be either 8 or 16. It cannot be anything else, right? It's either 8 or 16, but nothing else. By the way, this is the only timer in this hardware that can actually change from 8 to 16. The rest of the timers are fixed to 16. So we're going to just learn about that in a little bit. All right, so here we go. So if we finish what we were talking about in the previous problem, right? We calculated the 0.2 microseconds. If I want to calculate now the time of overflow, you just simply have to calculate 2 to the power of the number of bits, and by multiplying it times the number of cycles, or the frequency, or the period of cycles, you're going to get the final overflow frequency. So, period, sorry. So T0F is going to be T0C times 2 to the power of n. So this is going to be 0.2 microseconds times 2 to the power of 8. So that's going to be 256. So that's going to give you 51.2 microseconds. That's how often that circuit is going to overflow. Okay? So that's the speed of overflow. So what do you got? You just have a timer, and this timer is going to run out of numbers. That's all you have. You can make this timer go faster, or you can make this timer go slower, right? So what you are creating is a device that has the ability to overflow. Now listen to this carefully, because this gives you the idea of how you use this. The timer gives you the ability to predict an event in a circuit, right? I have the ability to create an event in a predictable pattern to the microsecond. I can choose this processor to alert me of an event every so often, and I have control over that often. Does that make sense? So you can create a clock. You can create a watch. I can create a frequency counter. I can create a revolutions per meter counter. I can check for acceleration. Anything that is time related, I finally have the means to do it. All right? Does that make sense? The only problem that I have with this is that you have a limited number of pre-scaling values and only 2 different sizes for my counter. You don't have infinite variability. Does that make sense? Okay, so let's pick this one. Try that. If I give you a pre-scale equal to 16, a frequency of oscillation equal to 20, and an n equal to 16, calculate the cycle time and the overflow time. Go for it. So here are the formulas again. All right, what's the first one? We got 4 times 16 divided by FOSC. So 4 times 16 divided by 20 million. What do you get?
3.2 microseconds.
3.2 microseconds. So this number, always remember, right? I'm just repeating this to make sure that you keep it in your mind. This is 3.2 microseconds per cycle, per timer cycle. How fast is the timer moving? All right, this guy is going to be 3.2 microseconds times 2 to the power of 16. What do you get?
210 milliseconds.
210 milli or 2.10 milliseconds?
210.
209.7, very good, right? So that's about 210 milliseconds, give or take. All right, so that means that every 210 milliseconds, this microprocessor will overflow. It will go to the point that I can't count anymore, and I will go back to 0. Now, here's the kicker. This device has the ability to detect that event and create an interrupt. And that interrupt is the one that's going to drive us. Because that interrupt now, I can use it for anything. Like I can use it to update a microprocessor. So for example, when a heart rate goes out of rhythm and you have a machine that is going to put that heart back in rhythm, they put it on a timer. Because they know that this device is going to be accurate to the microsecond. And I can detect exactly when I want to send a shot back into the heart. So you drive these things out of timers. Like for example, we were working on a machine that is sending medicine through gaseous means. And what we have to do is that we have to sample the amount of medicine that is going into the lungs every so often. So we do it out of a microprocessor with a timer unit on it. Why? Because I want to guarantee that if I am going to sample medicine, it has to be sampled at the right moment in time. I can't put it on a delay and hope that it will get there every 20 milliseconds or every 30 milliseconds. You don't have that luxury. It must be done every 20 milliseconds, right? So when you want to guarantee that something is going to be done in a timely manner, you put it in the timer interrupt. Does that make sense? And there's all kinds of different ways of going about it. So here we go. Here's my calculation. 4 times 16, so I like to put them in there so that you can actually down the road have something to just refer back, okay? This is a very common problem in the exam. It's going to show up a couple of times in the test, okay? So make sure that you look at this. Now, one of the best things that you could do to really understand what's happening in this system is to create a little spreadsheet for yourself, all right? What I have in here is the available prescale values for Timer0. So you have prescales of 1, 2, 4, 8, and so on and so forth, all the way to 256. And you also have the cycle time. So in here, what I'm doing is calculating 4 times the prescale value, which is this number, divided by the frequency of oscillation. I have it right now set up at 20 megahertz. What I'm trying to say to you is the following. Now pay attention because this is going to come back to haunt you in the test, okay? Now listen to this carefully. This is really easy when you are working from numbers that I give you to a time of cycles. But what happens when I give you or I ask you to give me a cycle time? And then you have to design the software for it. Here's what I'm trying to say. If I ask you, I want a microprocessor that can cycle every 3.2 microseconds, the answer is an N of 8, an oscillator of 20 megahertz, and a prescale of 16 can achieve that number. You see what I'm saying? Every one of these boxes require 3 things to be just right. The crystal, the number of bits, and the prescale value that I selected. But what if I ask you to give me 3.0 microseconds? What's the answer to that problem? The answer is you can't. I can't give you 3.0 out of Timer0 on an overflow circuit. I can't do it. Why? Because I'm falling in between the gaps. See that? So evil teachers, usually, In the test, they give you one problem where I give you N, FOSC, and PS. And then I ask you to calculate T0. And in the next problem, I tell you, set me the microprocessor so that T0C is equal to, and then I give you a number. See that? Now, why am I asking you to create an Excel spreadsheet? Because one of the best things that we can do as engineers and technicians is to gain an idea of what the circuit is capable of doing. See that? So, homework, all right? Make sure that you go online and set up a frequency prescale TOC table and start to get acquainted with which values I can get. Check this out. If I do this, so let me do something here quickly. If I change this to 16, look at the adjustments on everything. Whoop, it didn't adjust it, huh? Oh, because DOC does not depend. DOC does not depend on N. Right? DOC does not depend on N. My bad.
Only the frequency.
Look at this. It only depends on the frequency. So let's change frequency to something else. If I pick a 10 megahertz crystal, so let's pick a 10 megahertz crystal, then you can see how all your values change. Look, if the crystal changes to 10, my PS16 gives me 6.4 microseconds now. See how that works? Now, here's the practical part of it. Crystals, in general terms, are actually soldered onto the circuit. So if you want to swap a crystal, you're going to have to desolder and solder back in. That's not an option, right? That's definitely not an option. So when you're messing around with your timers, the only thing that you really truly have available is your prescale value. That's all you really truly have. Does that make sense a little bit? Okay, here is the T0F. So this is 2 to the n times this guy. And so working at 20 megahertz, this is the overflow times that you can expect, all the way to 3.3 seconds when you are at 16. So from 1 point, this is bigger, smaller, smaller, 13.1 milliseconds, all the way to 3.3 seconds is the kind of like range you can get out of 16 bits. You see where I'm going with this, right? What you're supposed to look at this table is not that I'm supposed to learn this. What I'm asking you to do is, when you're working on your labs, and when you're working on your quizzes, have this table with you. It's going to make your life 1,000 times easier by just having this with you. Okay? So make sure that you build this. So when the class is done, I'm going to ask you to build this in Excel. So we're going to do it together. Okay? So we're going to get this little table built. Any questions so far? Does that make sense? Okay, so how do I control this timer? Here is the register you need to know. It's called T0con. So there is a chapter that is all dedicated to Timer0. So I think is chapter number 3 is chapter 11. And so you have a bunch of circuits. The T0PS circuit, these three together, they choose my prescale value. This PSA is also prescale related. Then you have the T0SE and CS. The CS is very important. That's the source select. This is the number of bits. And then finally, you have the timer on, timer off. So this slide is for you to keep it as a kind of like a reference, because this is what you need to add in your library. So your library will require this. All right? Make sure that you know how to build these things, because in the exam, in the first 2 exams, I always ask, how do you take a structure and you put it onto a register? So make sure you know how to get these guys done. All right? I'm making the assumption that we're good at it, so I'm kind of like giving you already the answer. But make sure you know how to do this, because in the exam, I will be asking for this. It's usually 10 points. Okay? So
would you want us to write that out on like a piece of paper?
Yes, I will actually, what I'm doing, usually what I do is that I pick a register that you've never seen before. So I give you the entire register data sheet and I say, build me a structure for that register. And I'll let you go ahead and do it. And so usually I pick one that you've never seen before. So it's a good skill to have, especially for us that we're learning how to handle microprocessors. Okay? But here's the T0 con. This guy is going to control the entire behavior of the circuit that we just built. So it goes like this. I put in here this just as a reference. I just want you to have it. But what we're going to be doing is that I am going to be taking the circuits that are important to us. Okay? So I'm going to give you a little quick list of all the circuits that we really, really want to mess with. Okay? Here's what happens. It goes like this. How do you turn the timer on? So that's the first one. One. How do you go about taking timer 0 and turning it on? Okay? Here's the answer. You take inside of T0 con, you're going to find a timer 0 on, and you're going to make that equal to 1. So this instruction will never change. It's always going to be like that. If you want to use timer 0, you got to have this guy. Please remember that this assumes that you have already the structure that we talked about in the previous slide, right? The second thing you need to do is choose the bit length. Will you have your counter at 8 bits or will you have your counter at 16 bits? So 2 is bit length. And this is 8 versus 16. And here are the instructions for it. So it's going to be T0 con. And then you have your T0 8-bit. And then you can choose the value that you want. If you make it 0, that's a 16-bit choice. If you make it 1, that's an 8-bit choice.
So the X is,
You can pick the, you pick the value. So X is either 0 or 1. So if you choose 0, the machine goes to 16 bits. If you choose 1, the machine goes to 8 bits. That's what the capital N is in your calculations, right? That's what in your math becomes N, capital N. Now this one is the source select. So for us, there is 2 ways of driving the counter, right? You remember that when we were in Digital 2, I kind of like hinted to you that you could drive your counters out of a 5x5 or a signal generator, right? The counter will not see the difference between them. The signal generator can drive it. It turns out that this guy could be driven by 2 different systems, either with the crystal, the way that I show you, or by an external pin. I can go to an external pin and drive it. You can actually drive these guys with an internal oscillator as well. So there's all kinds of different ways you can drive this system. Here's what I need to tell you. This line of code will never change as long as we are in this class. Okay? We're going to be driving this counter in the same way every single time. So this instruction is a must, okay? T0 con, this is my internal structure cycle, and this T0 CS is the T0 clock pin, which is an external pin. So what we're going to do is this. Number 3, source select. Here's the one that I want you to go. It's T0 con arrow, and we're going to be using the 0 cycle. So this T0 CS equals 0, and this guy would never change. This selection is what makes this true. This is the reason why we have a divide by 4. And when we go to compare mode, it will explain why the divide by 4 is so important. Okay? So if you really think about what I'm saying here is that this instruction cannot be changed. Because if you change that instruction to a 0, you turn off the timer. So you don't want to do that. So you got to turn it on. In this one, you have a choice. You can choose 8 to 16. In this one, you do not have a choice. If you change this line to 1, all the math that we learned today will not work. You have to change the math. It's got to be something else. So in order for our math to work, you are forced to put a 0 on that circuit. See that? So if you see here on the board, I am forcing you to drive that instruction on every single one of our pieces of software, okay? Still here with me? These are the 3 most important selections that you have in this particular circuit. There is one more selection, and it's kind of weird. So I need you to just pay attention. Just shrug your shoulders a little bit, and here we go. Every single semester, students lose points right here. Right here. Why? Because it's tricky, okay? Here's how it goes. Every time you're going to choose a prescaler, the way that the prescaler has been selected is through a multiplexing system inside of the circuit. You remember multiplexers. You guys love multiplexers. Right after calculus in the morning, you guys practice multiplexers. So here we go. If you remember what is a multiplexer has multiple entry points and one single output, right? So let's say that you have 2 entry points. Did I draw this the right way? No, I didn't. So I'm going to draw it this way. So 2 entry points, 1 exit point, okay? Up there, I'm going to be calling this guy 1 and 0. So I'm going to call this guy 1 and this guy 0. There is a problem in the data sheet, by the way. The data sheet has these things backwards. I'll explain this in a sec. But what I have is that this is input 1. So input 0 and input 1, right? And they're labeled by 0 and 1. There is a selector. And your selector is going to choose who goes to the output. Okay? So if the selector is 0, then input 0 goes to the output. Now, remember that when you were in Digital 2, that selector was actually chosen through voltage levels. And now, in Micro, those selectors are chosen by software. See that? You can reset a pin to make this guy go to 0, which then forces the output of the multiplexer to be driven by input 0. See that? If the selector is equals to 1, so if the selector is 1, you set it, then the input 1 goes to the output. Right? If you remember how we talked about multiplexers in Digital 2, it was kind of like the train switch. 2 train rails coming in, 1 switch, and I can make 1 train go to the output, right? So 2 trains coming in, only 1 rail coming out, and I have to choose which of these 2 trains are going to go to the output. It's nothing more than a multiplexing idea, right? Okay, now here's the deal. Here's what happens. If you think about how this was laid out, you have a prescaling circuit. This is the circuit that has the ability to divide by 2, divide by 4, divide by 8. How do they do it? Here's how they do it. If you think about the FOSC divided by 4, this FOSC divided by 4 is the clock source selection that I showed you just a couple of minutes ago, right? We use this instruction for that. T0 con arrow T0 CS equals 0. And this is what chooses FOSC divided by 4, right? Which means that is T0CS. If that circuit has a 0, then FOSC divided by 4 is represented on this line. See that? You see it? I mean, your silence is so reassuring.
There's a lot of other stuff.
Yes. We'll get to those in a minute. So, if you make this T0CS equal to 0, FOSC gets represented at the output of the multiplexer, which is exactly what you did here. Which is exactly what I've been trying to get you guys to understand. Every instruction you make actually creates a physical change inside of the circuit. And that physical change in the circuit is going to now change the behavior of my circuit. So you are learning to program by behavior. I changed a line of code and the behavior of my circuit is going to change. The beauty of it is that it always changes in predictable ways. Right? That's the idea behind it. Okay, so now watch this. So after you have that instruction, there is another instruction that is required. But I want you to notice that the pre-scaling circuit could be completely bypassed. See that? There is a bypassing device. If you think about the output of this multiplexer, the output of that multiplexer either comes from a pre-scaling circuit or not. I can choose which one I take. You see that? Here's why that is important. The reason why that is important is because if the PSA circuit has a 0 on it, the program prescaler is going to drive the ultimate output. But if the PSA is equal to 1, that means that I am going to choose my output and it's going to be represented by the crystal divided by 4. In other words, there is no prescaler online. See that? If there is no prescaler online, it means that you divided by 1. In other words, you did nothing. Right? What is divided by 1? Nothing. Right? So how do they achieve a divide by 1? Is by bypassing the prescaler. But here's what happens. And here is where I am going to take some points from you. All right? Now, if I don't tell you this, and you miss points, it's my fault. But I told you about it. So if you miss points in the test, it's your fault. All right? Check this out. Listen. If I take a PSA that is bypassing the prescaler, it really doesn't matter what my instruction for the prescaler is. At the end of the day, the prescaler is offline. So you can kill yourself writing a whole bunch of instructions for that box. If your PSA is bypassing it, you will never see that behavior at the output. See that? It sounds difficult. It's kind of cryptic. It's very easy. I have a box. You can send instructions to that box. If I bypass that box, your instructions are for naught. Right? Pretty straightforward. So, if you go back to the list that we already started, we got 3 instructions. Timer on, bit select, source select, right? Those are the 3 instructions I gave you. Timer on, bit select, source select. We have those 3 done. What we need to do now is choose our PSA. So, here we go. If you want a PS equal to 1, you want that prescaling box to give you a divide by 1 value, I want you to write that instruction, and that instruction only. And your system is done. You're done. Okay? So, it will look something like this. For a prescale equal to 1, you're going to have T0 con, TMR0 on 1. You're going to have T0 con, R08 bit, I think we'll go T08 bit, equal to, you choose the bits, either 0 or 1 for 8 or 16. The next instruction is going to be T0 con, T0CS equals to 0. That's always 0, because we want the FOSC divided by 4. And then we do T0 con arrow T PSA equals 1. And that gives me a divide by 1. All right, notice this. That's a divide by 1 choice. Okay? Now, if you want to divide by 2, I'm going to go back in one slide. Right? If you want to divide by 2, the only device that can divide by 2 is the prescaling circuit. Right? So what you need to do is that you got to make sure that you tell this guy, please divide by 2, and at the same time, you have to not bypass that circuit. I got to switch from a 1 to a 0. You see that? So the instructions are going to show in pairs. So if you want to divide by 2, 4, 8, 16, 32, 64, 128, or 256, these instructions always show up in pairs. You cannot have only one instruction. They got to be paired together. Right? So look at this. This is a divide by 2. You have to not bypass, choose divide by 2. See that? Not bypass, choose a divide by 2. Are you here with me? In the data sheet, a divide by 2, they actually show you a divide by 2 by writing it like this. Is 1 dot dot 2. That means a ratio of 1 to 2. You guys see that on the computer? What about this one? So divide by 2 is 1 ratio to 2, like that.
Okay, that's better.
Okay? So if they say a divide by 4, they go 1 colon 4. I say a ratio of 1 to 4. So divide by 2, 4, 8, and 16. You always have to give me a pair of instructions. Always show up in pairs, right? Now, here's what I want to tell you. Check this out. If you do this, watch this pair of instructions compared to the pair of instructions in there. Look at this. T0 con PSA of 0 versus a T0 con PSA of 1. See that? You have a T0 con TOPSX to 0 against a 0. So 0 against 0. This is a divide by 2. This is a divide by 1. See that? If you want to divide by 4, watch it. A divide by 4 forces the PSX to be 1, while the PSA is still 0. Now, if I just come down here and I change this to 1, there is no behavior change out of the circuit. The circuit remains the same. Why? Because I am bypassing the whole circuit. And it doesn't matter how many instructions you put in it, it will never change. See that? Every semester, I marvel at the fact that I say this in class and I still get to use my red pen in that question. Which is like, still do not understand. So, this semester is the semester. I'm not going to use that red pen this semester. We're all going to get perfect in that problem. Always watch carefully. If I am bypassing the prescale, it doesn't matter what I put in this prescale, you will never use this value. It is a divide by 1. See that? It just brings me so much joy to make the problem and then so much grief to start using the red pen, even though I said it. How many times I've said this now? 3 times, right? That's the surefire way of you knowing that I will put it in the test, right? I know the guy who makes the test, so I know it will be there, okay? So pay attention to this. This is a very typical problem that you see in all microchip picks. They have a bypass for the divide by. Okay? Any questions on that? So your setup, it always looks like this. It's going to be timer on, bit select, source select, prescale bypass, prescale value. So it's always like that, always, every time. So I wrote it in here for you. It's just the same thing I just said. You don't even have to note it down. You're gonna have this in your slides, so you can have it. It's always the same thing. If you want to set up the overflow circuit, timer on, bit size select, source select, bypass option. If the BSA is reset or 0, then you choose the desired prescale value. That's it. And the code looks like that. We already wrote it in the board. I'm just here reminding you what the code looks like. Inside of your main, you're going to have these 5 instructions, and then those X's means that you got to go to the data sheet and choose the value that you want. Right? That's all that means. Whatever value you want, you'll choose it. That's it. Okay? Any questions on that? I mean, I see your faces of excitement. This is so awesome. This is so great. Right? All right. Here's the part that is important. This is the interesting. This is the culminating factor. When you want to interrupt, the event that interrupts this circuit is an overflow event, right? When the timer wants to count, but it can't count anymore. When that event happens, my interrupt vector called #int_timer0 will trigger. And I have the option to do something about it. You could do whatever you want about it. For the latest project that I ever built, every time this interrupt triggers, I take a sample out of the medicine that is going into the air intake, just to make sure that I am taking proper samples on parts per million going inside of that patient's lungs, right? This machine, we actually built it for people that have heart disease. When they have to breathe, they actually throw medicine into their lungs to actually dilate their bronchioles so that they can accept oxygen in an easier way. They use this also in neonates, kids that are born with 30 weeks, 20. I've seen kids using this at 23 weeks. I have seen a kid survive at 20 weeks. And so they take this medicine and they put it in a bubble and they deliver it to the baby and they open up their airways because their lungs are not well developed. And so the medicine opens up their bronchioles and they can breathe better even when their lungs are not completely fully developed. And that technology has been created right here in Madison, Wisconsin by a pair of guys from Britain that has been here for about 20 years. And these 2 guys have disrupted the medical community. It was just a privilege to work with those guys. So, and it was fun to see how this medicine is being used for kids that people will otherwise believe that they will not survive. They put it on this medicine and it's absolutely amazing. I love the biomedical world and I'm just a programmer. I just program stuff. And so it's fun to see. All right, anyway, so that's your interrupt vector. The interrupt instructions, which is remember that you can have a timer and you could have an interrupt with it. You don't have to put these 2 together. However, a timer without an interrupt is like a car without wheels. And if you're going to use a timer, you want that interrupt. So to set up the interrupt, there's only 3 instructions. All right? They are all located in int_con0. All right? So they're all located in int_con0. So there is my int_con register. So I put here in color these blue ones. Those are my overall interrupt enable bits. One is called the global interrupt. The other one is the peripheral interrupt enable. And as you remember, the external interrupts and the analog to digital interrupts have the same 2 instructions. So every time you have an interrupt in this system, we're going to put those 2 instructions. So this guy, int_con PEIE equal 1 and int_con GIE equal 1, those are the 2 instructions that we always have. Every time you hear the word interrupt, boom, those 2 instructions have to show up. The instruction that's different is the first one. Int_con timer0 IE equals 1. That's that reddish looking circuit. If you make that circuit equal to 1, the vector that you just set up will trigger. What I mean is this. This guy will be physically enabled only if this guy is physically enabled. See what I mean? So if you want the system to interrupt, you have to make sure that those two things are set up right. Okay? The instructions look like that. So here's your code. Let me see if I can make this a little bigger. Because it looks very small on these slides. Better?
Mm-hmm.
All right, so here we go. Pre-processing commands, you're all used to these pre-processing commands. Every single one of your problems this semester has the same line, so you don't have to worry about that. Next comes the interrupt service routine. This is the int timer0. So this guy is the one that is going to trigger. You have the interrupt service application. So in there is where you write your novel idea, whatever you want to do in there. So like I said, we've been doing this for, we have a client that has a stratospheric balloon. And so that's what we use to navigate. So every so often I want to take a sample of latitude, longitude, speed, altitude. So I want to know where I am. So every so often I'm going to take a sample of all my systems and I put it in an interrupt. That's where that goes. If you want to put medicine and you want to check the medicine, that's where the medicine checkup goes. Notice that the actual setup software is the same regardless of your application, right? As a minimum, guys, as a minimum, what I really want for you guys to understand is that I don't care what application we're doing. If Timer0 is involved, that's how you set it up, regardless of what you're doing. Okay? Now, here's where the timer setup goes, and here is where the overflow interrupt setup goes. And it's just a matter of copy-paste. So the next slide is just nothing more than a copy-paste of what we've done so far. I just simply took the setup instructions, dump them in there, and I took the interrupt instructions, dump them in there, and then I set up my Timer0, and I'm ready to go. My system is ready for testing. All right, which is what we're going to do now. Together, we're going to set up this. All right, here's what we're going to do. I'm going to do something really simple. Okay, the idea is the following. I'm going to take our little microprocessor, and I am going to pick pin C0 as my center of operations. What I want to do is that I want to pick any prescale value you want. It really doesn't matter. Just pick any prescale value. I like to pick a prescaler of 1. Why? Because it's the easiest one to make. Right? I like easy. So we're going to make a prescaler equal to 1. So I'm going to work Timer0. I'm going to pick a prescale to 1. I'm going to take an n equal to 16. And I'm going to use the typical 20 megahertz crystal that we've been using so far. So that's going to be my setup. Just for the heck of the argument, I'm just testing that T0 works, okay? What I want to do is that every time my microprocessor interrupts, I want to toggle pin C0. Just toggle it. That's my application. That's it. My application is a pin toggle. Why? Because I want to see the circuit. That's it, okay? So here's what's going to happen. My T0 is going to be working at the same number that we did in class, which is 2.2 microseconds per step. Then I'm going to take my T0 flow, is going to be 2 to the 16 times 0.2 microseconds. And so then the period at pin C0, so the period at that spot is going to be 2 times the period of the overflow. All right? Okay, so what am I doing? What I'm doing is this. I have all the mathematics I need to predict what's going to happen to this micro before I put my hands on the micro. See that? That's the trick behind engineering design, is to attempt to know what's going to happen before you put your hands on it, especially on circuits that you have seen before. If it's a brand new circuit that you've never seen, by all means, this is hippie style. We just go in and see whatever happens, happens, and we'll just figure it out as we go. But when you deal with a counter, I mean, we know that's how fast the counter goes. That's how often it's going to overflow. 2 of these are going to create the system that I want, right? So, kind of like, I'm not so sure if some of you are going like, oh God, kill me right now. Or if you really understand it, but here's what happens. The oscilloscope is going to look like this. And the only way that this can toggle is if one of these happen. Right? So right at this spot, one of these happened and it toggled. And so if you really think about it, it takes two of them times 1 times 2. It takes two of them to force one full cycle. So the period at pin Z0 is twice the overflow because these guys are associated with this. Does that make sense? So just by looking at the application, really the application is nothing more than I'm going to let this guy trigger once, I'm going to toggle, I'm going to wait until it triggers again and I toggle again, creating one full cycle. So think about this. This is circuit related math. So this is setup circuit related. This math is application dependent. This is the application. So this guy, so this is the application. See that? So if I switch the application, right, like in a test, for example, this math remains the same. But that math can change. See that? So this math will change depending on the application that I choose. Remember that the application shows up here. The rest of the stuff is setup. So setup determines this. Whatever I write in here chooses the application I follow. Right? So that's the part, believe me, the reason why I'm saying this is because every semester I change the application and I get to use my red pen. I buy the red pen for these moments in life. I'm telling you, watch the application carefully. The application is what determines that. This is application dependent. While this is setup dependent. These guys will never change. Okay? Any questions? Concerns? Let's do it. Let's do this let's try this. All right, so I'm gonna build this software.